Hi everyone, I'm Miss Winslow, and today we're going to be covering a topic called literal equations. And to do that, we're going to recall how to solve equations and then, of course, solve some of those literal equations. So grab your notes and let's get started. So the first thing I wanted to chat about was what are literal equations? You might be used to seeing equations. So here's some examples of what we feel or what we think of as equations. Things like x plus 3 equals 8. An equation is when you have two sides set equal and they're balanced. So that means whatever's on the left is going to equal whatever's on the right. Another example that you might be used to, maybe y plus 1/2 equals 3 plus 2y. Here we have two terms with a variable in it, but it's the same variable. So traditional equations that we're used to have one variable, and the left side will equal the right side and vice versa. So the difference is literal equations have more than one variable. More than one variable, and you're going to see this a lot as you go forward in your math. So an example might be just something like x plus y equals 4. It still means that whatever's on the left is going to equal the right-hand side, but now we have more than one variable. An example you guys are totally used to, y equals mx plus b. This is an example of a literal equation. And look at this one. This one has all letters, but still, we know that whatever values we put in for these, the left is going to equal the right. Another example might be this one. You may have seen this in your math courses or even your science courses. Distance equals rate times time. Again, all variables, three different ones, and again, the left will equal the right. So literal equations are just a type of equation. Literal is an adjective to describe equations. So hopefully they don't feel too foreign or unfamiliar. So why are they even important? So here on this slide, I put some examples of literal equations for you guys. We already looked at a few on the other slide. But if you see, we have area equals pi r squared. That's area of a circle. There's a circular shaped item there. I love pizza. I need black olives on mine though, please. And just think to yourself, why would it be important to know the area of a pizza? I mean, I don't know if any of you and your friends or family have sat around to figure out, which piece is going to give you the largest slice, which pizza will give you the largest slice. Next time you decide to order pizzas and you're trying to figure out if you need a small, medium, or large, based on the number of people you have, you're definitely going to want to look at the area. Area of a triangle, perimeter of a rectangle. Here's that distance equals rate times time. Area equals length times width. That's really for a rectangle or a square, right? And then this one is really cool. This is the formula for tire pressure. And I actually have built into my car, which is nuts. This formula calculates automatically for me, and I get a notification if my tire pressure is below where it needs to be. So these formulas are all very useful in the real world. And they're very important because I just feel like they're most important because they give us real information. Real and useful information. Not to give regular equations a bad rap or anything, I just feel like literal equations are much more helpful. And that's because you can actually rearrange these to solve for the variable that's most important to you in that situation. For example, distance equals rate times time. Maybe you're not as curious about the distance. Maybe you're more curious about how long it's going to take. And so you can streamline things and make it easier for yourself and whoever's using the formula by getting t by itself instead of d. So speaking of, we're going to watch a quick video of the use of literal equations in the real world. So let's check this out.
Hello, I'm Professor Von Schmohawk, and welcome to YU. In the last lecture, we saw how linear equations can be used to solve real-world problems involving quantities such as ages and dimensions. In this lecture, we will see how to use linear equations to solve problems involving time, distance, and speed. Most of us are familiar with the concept of speed. We know that when we travel faster, we get to where we are going in less time. Or we travel a larger distance in the same amount of time. Automobiles come equipped with speed measuring devices called speedometers, which indicate speed in miles or kilometers per hour. The indicated speed tells us how many miles or kilometers we would travel in a single hour, assuming we traveled at a constant speed for the entire hour. Let's say that we are traveling at a constant speed of 50 kilometers per hour. We can visually represent this motion by graphing our distance from the starting point versus the elapsed time. If we graph time on the horizontal axis and distance on the vertical axis, we see that our distance increases at a constant rate. Distance is a linear function of time as long as our speed is constant. Our speed determines the slope of the graph. The greater the speed, the greater the slope. Just as slope is defined as the change in the vertical coordinate over the change in the horizontal coordinate, speed is defined as the change in distance over the change in time. If the change in distance and time are measured starting from the beginning of the trip, then our speed is simply the distance divided by the time measured at any point along the trip, assuming, of course, that our speed is constant. For instance, if we travel a distance of 50 kilometers in 1 hour, then our speed is 50 kilometers per hour. If we travel 100 kilometers in 2 hours, the calculated speed will still be 50 kilometers per hour. Likewise, at the speed of 50 kilometers per hour, we will travel 25 kilometers in 1/2 hour. Knowing this relationship between speed, distance, and time, we can calculate any of these three quantities if we know the values of the other two. For example, by multiplying both sides of this equation by time, we see that speed times time equals distance. For example, if we go 50 kilometers per hour for 2 hours, we will travel a distance of 100 kilometers. This formula is easy to remember and very useful for solving problems involving speed, time, and distance. As an example, let's say that we are on a train 100 kilometers west of St. Louis, traveling east at 60 kilometers per hour. How long will it take us to travel 290 kilometers east of St. Louis?
All right, I'm going to stop it there. First of all, how cool was that they related the linear function to the distance equals rate times time formula? They showed you how the slope is related to finding that rate. That was really cool because you guys are definitely familiar with linear functions and slope. And then we talked about the distance, the literal equation for distance, right? And why would we even care about this problem? And there are actual people who work for Amtrak and other train companies who will calculate the time it will take different trains and buses to arrive at different locations. One, they need to make a schedule, right, to sell tickets, and also just to coordinate those different vehicles coming into the stations. You know who else does this are air traffic controllers with airplanes and the schedules. So you can see, hopefully you can see that literal equations are very helpful in the real world. All right, so now we are going to actually practice and recall solving equations. This is going to help us get into the groove for our literal equations. And I know that you guys have done this a lot, and we're going to be working with inverse functions, right? So here, our goal is to solve for x. So we want to get x all by itself. Don't forget, at any time, you can pause this recording, try it on your own, and then come back for the answer. So in order to get x by itself, we're going to do the inverse, or the opposite, to plus 3. So we're going to subtract 3 from both sides. Now we'll bring down the x value, and of course 3 minus 3, that's 0. That's kind of the whole point, right? And then 8 minus 3 is 5. There we go. We solved for the missing variable. Let's look at example 2. Here is our term with the variable. So we need to get everything else away first. This is a minus 1, so we're going to add 1 to both sides. Bring down the 3y. Of course, these cancel out, and we get 14. And then in order to get y by itself now, we have to do the inverse of multiplication. Well, the inverse, or the opposite of multiplication, is division. And don't forget, fractions are okay. Fractions are actually more real. I feel like we see them more in real life than we do whole numbers. So it's totally fine. Just make sure you've reduced that fraction as far as it'll go, which we have in this case. All right, example number 3. So here's one where we have variables on both sides, and the t happens to be kind of stuck inside those parentheses. So remember, whenever we have a number next to a parentheses, we're going to distribute. So 2 times t and 2 times negative 1. We'll do the same thing on the right side, 5 times t and 5 times 2. There we go. So we want to be able to get all the t terms together and all the numbers together, right? We're going to combine like terms. So I'm going to bring this positive 5 over to the left by subtracting it and combine it with its buddy over there, the 2. So 2 minus 5 is negative 3. Bring down the negative 2 and bring down the 10. Now we're getting closer, right? This looks very familiar to the second example we did. To get our t term by itself, we need to first get rid of the 2 by adding it. All right, now to get this t by itself, we'll just do the opposite, or the inverse of multiplication. So we'll divide both sides by negative 3. And t is negative 4. Don't forget, at any time with these, you can always plug those back into the original equation, and the left-hand side will equal the right-hand side. Remember, that's what we said the definition of an equation is. All right, so let's solve for b. That means we want to get b all by itself. So I see 2b terms here, which means we need to do what we did similarly in that very last example, is collect like terms. So let's move the 3b over to be collected with this b. So this is a positive 3b, so we'll just subtract that from both sides. And I'll bring down my a. 1b minus 3b is negative 2b. Bring down the negative 3 and bring down the 1. All right, what else can we combine? Ooh, I see a constant here and a constant here. So let's get those two together. I am going to move the 3 over by adding it to both sides. So we'll have an a minus 2b equals 4. Now we're almost done. We are working on getting our b term by itself. So this is a positive a. So I'm going to subtract that from both sides, move it over to the right. And look, when you see this, don't let that freak you out. You're just going to write 4 minus a. That's totally fine. These are not like terms, so we cannot combine them. So you can just write them right next to each other. And lastly, to get this b by itself, we need to do the inverse of multiplication, and that is division. Now, when we're going to divide, you have to divide everything on the other side. It has to be fair. So you might see it written like this. Or you can divide each term, negative, by that number. And so you could leave it like this, or we could even reduce, right? 4 over negative 2 is negative 2, and negative a over negative 2 is a positive a. We just did that negative divided by negative. Both of these answers are the same. It's just that essentially in this one, they found a common denominator. All right, let's try number 2 here. I'm going to grab a different color. So our goal is to solve for t. So here's the t term, which means we need to get everything else away from it first. So we have a negative 2c or minus 2c, and the inverse of that is addition. So we'll add 2c to both sides, bring down t over 3. And remember, you can't combine these, right? They're not like terms. So all you do is rewrite them right next to each other. And lastly, in order to get this t by itself, look, we're dividing by 3, so the opposite or inverse of division is multiplication. So we will multiply both sides, everything on the right-hand side by 3. And I'm just going to pop it here in the front. Depending on what your teacher wants you to do, some teachers will have you leave it like this, and some teachers will have you actually multiply the 3 out. As you move forward in Algebra 1, you'll see the different times to use the different methods. So I'm going to show you both. We could just distribute this 3. 3 times negative 4 is negative 12, and 3 times 2c is 6c. So there we go. We solved the literal equation. We didn't get a single answer for t, right? We just rearranged the equation. We made it look different. We made it work for ourselves. Like maybe t is telling us the time and c is telling us the cost of something. So it would be more useful and valuable to us as a consumer to have it solved for t. How long is it going to take for me to earn enough money to buy this item? So I feel like that's the whole point in literal equations and rearranging them, is to getting them in the most useful form for whatever you're using them for. Let's do some more. This says solve for y. So y is right here stuck along with so many other things. Z equals 6 pi times x times y. So pi, which I know you've learned by now, is just a number. We usually shorten it at 3.14. And oftentimes you'll see pi left as pi. Like you're not going to see 6 times 3.14 where they actually multiply it out. They'll just leave the symbol pi. Because that way, you know, pi goes on forever and ever and ever, right? So this way I say they, the test writers or you guys who are doing the problems can get all of those significant values. You're not going to leave anything out by rounding to the hundredths place there. So oftentimes you'll just see them leave pi. So that's what we're going to do. We're going to get y by itself. Now look what's happening over here on the right. We're multiplying everything. 6 times y times, or 6 times pi times x times y. So to get rid of 6, pi, and x, look, all we have to do is divide, right? The inverse of multiplication is division. Because 6 divided by 6 is 1. Pi divided by pi is 1. X divided by x is 1. That was fun. So you're left with y on the right-hand side all by itself. And then this is over here. And I know that it doesn't look very pretty, but it's okay. You solve for y, and I don't have a particular example for this formula, but whatever it is, y was more important to us for some reason, and we wanted it by itself. It just makes the formula more useful for our purposes. Here's another one. Solve for b. You can see this equation has not a single number in it, and that is okay because the numbers behave really similarly to the letters. So we know how to do this. You know how to do this. You can do this. All right, we're trying to get b by itself. For now, b is stuck. It is stuck connected to the c inside the parentheses. So whenever anything is stuck, we should work to get it unstuck. And the way to do that is to go ahead and do, hopefully, what your gut is telling you to do. Whenever you see something in front of a parentheses, we want to distribute it. It's just our natural feeling. A times C plus A times B. equals D plus. There we go. We got the B out. Now B is part of its own term. So we can start working towards getting it by itself. So let's move the AC term. It's a positive AC. So this is a whole term in itself, right? And it's connected by addition. So that's why we're going to subtract it. I didn't want you to think we were going to divide because A is being multiplied by C. That's true, but it's connected to AB by a plus. So that's the inverse we're going to do. Bring down the AB, and we just have D minus AC. We're really close. We're trying to get this B by itself, and this is A times B now. See how this is the only term now? So it is just multiplication. So we will divide. And you get B equals D minus AC over A. This is definitely a more simplified version than doing this. Some would say. And some would say this is more simplified because then we can cancel the A's. So it's kind of up to you for our purposes right now. As you move forward in math, you'll be given more explicit instructions on how you want to leave it. But whatever you do, when you're doing this division or addition or subtraction or multiplication, just make sure you're doing it to everything on the right-hand side. All right, here's another one. This tells us we have a formula for a trapezoid related to the area A. And then we have two bases, little a, little b, and the height h. Solve for little a. So I want to tell you, all of this information here, that's great. It's nice to know the background information, what you're working with, but do we really need it? Do we really care? Not really, because our goal for this particular problem is just to rearrange it, just to solve for A. So it's nice that they told us it's a trapezoid, but I don't want you guys to get bogged down in all that language and then get discouraged. Like, what are they asking me to do? Okay, solve for A. I got this. We're going to get A by itself. Now, we see some parentheses. So there's kind of two ways to solve this problem, and I can show you both. That's the really cool thing about math. There's always more than one way to solve a problem. So let me grab a different color because I'm getting tired of red. So if you look at this, we have a fraction times h, some number h. So we know that the inverse of multiplication is division. So we could get rid of the h by dividing both sides. Or if you wanted to, we could take the h and distribute it. Because this is really h over 1. So let's distribute the h. I don't know. Whenever I see parentheses, I just have that feeling that that's what I should do. But again, it will work the other way as well. So we have A equals h times A plus h times B over 2. All right, it's looking a little bit better. We got rid of those parentheses and took care of that h. Now check it out. We have a big fraction here. So we're dividing by 2. What's the inverse of division? I'm going to get a different color. It is multiplication. So we're going to multiply both sides by 2 in order to do that. Kind of like they did in that video. Remember where they crossed out time? All right, so we have 2a, big A, equals little a h plus little b h. All right, what's our goal again? We're solving for A. So I'm going to circle or square my A term. So let's get rid of the BH term. This is plus BH. So the opposite of plus is minus. Cool. So we have 2A minus BH equals AH. These go away. Now our very last step to get little a by itself. This is A times H. So the opposite of times is divide. Just do it to everything. And you're done. We can rewrite it if you want with A on the left. That's just kind of how you see it, right? Awesome job. I feel like this is probably one of the harder ones. And did anybody else feel like you were like talking in another language as we were going through that? Like 2A, 8H, little b, little h. Kind of fun. So there's our answer. And for some reason, for this trapezoid, we are finding it more helpful to have it solved for one of the bases for that particular purpose. All right, here's our last example. Here's the formula for determining how long a hike will take. I'm going to rewrite it. And then they give you some information, right? That really doesn't matter for our goal, but it's good to know. D is the distance in miles, and H is the elevation gain in thousands of feet. So when you think of elevation gain, I'm thinking H stands for, height. How high did you walk? Solve for D. So check out our D. Our D is stuck. It is stuck inside the parentheses, and whenever we're stuck, we want to get out to solve for that variable. So we have a number in front of the parentheses. We're going to distribute it. Don't worry that it's a fraction. 1/2 D plus 1/2 H. Here we go. We got our D term out. Here is our D term. So let's start getting rid of everything else and getting D by itself. So let's subtract the H term from both sides. You end up with, I'm going to come over here, T minus 1/2 H equals 1/2 D, right? Because those canceled out. 1/2 minus 1/2 is 0. And that's the whole point, right? In order to get it to the other side. All right, lastly, to get our little d by itself, this is 1/2 times d. So you can definitely divide both sides. I mean, that's the inverse rule, right? When you're multiplying, the inverse is division. But also, when we're doing a fraction, you can multiply. It's not really the reciprocal, but you flip it. A reciprocal would be, flipped and negative. Here, we're just flipping. And it's kind of just another way to divide by a fraction is to multiply by it flipped. So we have, and the reason this works, and I can kind of bring them together here, is because 2 over 2 is 1. So that's why they cancel. It's fun to cross them all out. All right, so once we had fun crossing all those out, we're also going to multiply this side by 2. Remember, you have to multiply both sides by the same thing to keep it fair. So we're going to end up with little d equals 2 times all of this. And I'm going to leave it like this because technically that is the most simplified. I don't know, you might have some people tell you to distribute it, and it's not a terrible idea. We'd have 2t minus h, actually, because those 2's would cancel. So again, you'll definitely get more direction as you move on in math and which form you're going to be using. But thank you guys for sticking with me today, and I hope that you found maybe a new purpose for literal equations. Bye, everybody.